who will talk about development of regional high resolution hydrodynamic models in estuarine regions, so the Seine and Elbe cases. Thank you.
Well, thank you. My name is Ramiro Ferrari from Noveltis, and I will present two regional model study case, one in the Seine estuary in France, and the other ones in the Elbe estuary in Germany. This effort was shared with people from Lagos, from University of Oran, University of Bonn, ESA-ESRIN, and Vortex. Well, the objective of this work is, is to obtain sea surface elevation field, an acquired sea surface elevation field to be used as a calibration, and validation, and correction of the satellite altimetry, mainly Sentinel-3 and SWOT over this estuarine region. As we know, the estuarine region are very complex, have a dynamic circulation that is very complicated, very complex. To obtain an accurate sea surface field in the estuarine region, we have to know the component of the river, tide, surge, along altimeter ground track. And to obtain this information, that it vary very strongly and very quickly, in terms of centimeters and a few minutes. We need a high resolution regional model. The requirement of the high resolution regional models are a well-defined coastline, good accurate bathymetry, geoid also to be used as a vertical reference. Also, we need some take gauge EC2 data to be used as boundary condition, assimilation, and or validation. Finally, we need to know the component of the tide and surge in the ocean side. So the first case is the Seine estuary, development of the model in the Seine estuary. This work was made in the frame of the streetcar project that was presented by my colleague Elodie yesterday. For this experience, we use Toulouse and structure grid model developed by Lagos, as we know, two models. And we use a mesh grid resolution mesh grid of 4 kilometers in the open ocean to 25 meters upstream the same river. Also, we use 18 tide gauge as a boundary condition, assimilation, and validation from the French hydrography service from Schwab. And also we use in the boundary condition of the ocean side phase 2014 for have the tide and surge information as a boundary condition. So in terms of bathymetry, we test, we made several tests, and we test the bathymetry from Lagos, developed in 2017, and also the new homonym bathymetry of the Schwab. In terms of performance, we didn't see any significant difference, so we continue to working with the Lagos bathymetry. Also, we test different coastlines. The last coastline of Schwab, I can show you in blue, and in black. You can see the coastline of the developed by Lagos in 2017. And also, as with the bathymetry, the several tests we didn't that we made in this region, we didn't find any significant difference. So we keep continuing with the coastline developed by Lagos. So once after hundreds of tests, once that we found the optimal model configuration in terms of viscosity coefficient, bottom friction, bottom rugosity, lateral friction, etc. parameters. We made several tests. Here I show you the errors in meters for the different tide gauge station. In red, you can see the errors in comparing the in situ data at every station with the free run model. It means that it's not we didn't assimilate any tide gauge in situ data. So the results are very encouraging because we have errors smaller, mainly the most of the errors are smaller than 25, 30 centimeters. That these errors in the this estuary region are very good. But we have in the neighbors of the ASIR station, that it's just here. It's more complicated dynamic in this region, and we obtain errors of 65 centimeters. And also we have made the other colors line means that the errors of the others test that we make with different degree of in situ data assimilation. It means a larger R mean less constrained model. So, for example, you can see in the blue with the errors with the blue line is the most constrained run that we made, and if we compare the errors of the most constrained run with the free run with no assimilation run, we can observe that we have at least one order of magnitude smaller. So here I show you an example of the time series for on-floor station. It's the first one in the mouth of the Seine estuary. You can see in black the elevation for the in situ data. In blue, the elevation also for the most constrained run test. And in red for the free model, the free run model output. So the results are very good, very encouraging because they reproduce the model reproduces this feature. This feature is not it's the effect of the river interacting with the tide. You can see that it's not the regular tide waves, and we have this kind of feature that is the most difficult to reproduce for a model in the estuary. So this feature, as we go as upstream the Seine River, became more and more evident. So finally, I show you a test that we made to compare what's happened if we relax in some station. In this one, we made we relax in 5 stations. Compare with the entire constrained model, and in blue is also the most constrained model errors. You can observe that as in red is the relax relax and constrained model, and you can observe that here, and here, that as we relax the model in some station, the errors are triggered. So it means that the dynamic is very, very local. And if we want to obtain model outputs of any centimeters with an error of any centimeter, we need to assimilate as tight gauge as possible. So for the ELBA history, this work was made in the frame of next contract, and we use also two model developed by Legos. We use mesh grid courtesy of the University of Bonn. The bathymetry is from Waterways Institute, German Waterways Institute, and University of Bonn. And also we use geoid from the German Federal Agency for Cartography and Geodesy. In terms of pulmonary condition, we use also in the ocean side phase 24 to obtain the tide and surge information, boundary condition. And we use in the upstream Elbe River the boundary condition of the GISTAC tide gauge in situ data as a boundary condition. Also, we have 25 tide gauge for in the entire estuary to use as a simulation validation. So with this configuration, the bathymetry, the vertical reference, and the mesh grid, we made hundreds of tests to obtain the optimal model configuration, finding the viscosity coefficient, bottom friction, bottom rugosity, etc. And the results are very, very, very good. Here I show you with red circles the errors between the in situ data, the 25 station, and the free run model outputs with the configuration that I show you in the last figures. And we can observe that the most of the errors are smaller than 15 centimeters. That is very good, except for these two stations. That's the problem. These two stations that we have kind of split barrier that inputs a very difficult dynamic in the Elbe flow that the model can reproduce. So what we are working now is to make the different quality tests with the tide gauge assimilation as in the same history. To conclude, well, these two experiences show very encouraging result to use the model outputs as CalVal and correction for the high frequency altimetry in this region. But well, however, this model require almost in the same as show the same experience to assimilate as tight gauge as possible. Well, based in our results and in the experience gained in this work, we are ready to attack another region for the CalVal activities. Of course, the model outputs and the data are ready to start to play and compare with the compare and correction the high resolution altimetry data in this region. Thank you for your attention, and if you want to contact me, I'll give you an email address.
Okay, thank you, Ramiro. Any questions to Ramiro? If you don't have some, I have several actually. The first is concern the morphologic evolution of the river and also the river mouth. We know there is a lot of sediment transport and river discharge. This will modify locally bathymetry, which is the important parameter for tidal modeling. Is it foreseen to have a separate configuration with bathymetry that is evolving due to sediment transport or something like that? Is it an important...
We didn't active the sediment transport. The model have a configuration to active the sediment transport.
Okay.
But I think that your question is if we assume that the bathymetry is a statistic.
Okay, it's okay.
Yes, in this test, yes, because well, I know that the bathymetry are right. We have the bathymetry, the high resolution bathymetry, the best bathymetry that we can obtain, but well, we don't know if the bathymetry in some regions it's very accurate or not. So
okay,
we prefer to be conservative disactivate this model.
Okay.
I can comment on that.
Yeah.
So in the website that I addressed to you, there were at least 10 bathymetry in the past. I think that you used the last one. But in the Elbe, they are digging a lot. So it will be, probably the one is not anymore, but it's really a problem. They wanted to extend the port.
Yeah.
But hopefully it will not be important, but it's evolving anyway. Yeah.
Yes.
Yeah. In this model, you have no salinity, you have no anything.
No, it just
because the one that I showed today is not so good, but you have bathymetry, you have salinity, and I think also something with perhaps using also this one could be helped to compare.
Yeah. Also, I was thinking, but also we make several tests, but here I show you the result of 1 month model run. So I don't know, didn't know very well the dynamic of the sediment in this in the mouth of the ESA-ESRIN, but I don't know if it's in 1 month can change a lot of significantly to change the, I don't know, the bottom drag or the lateral friction, but we are quite limited for the bathymetry informations.
The bathymetry data that you are using is available globally or locally?
No, it's locally. It's in the General Federal Waterways.
And what is the spatial resolution?
Do you remember? No, I didn't remember. No, I didn't remember. Okay. But the bathymetry resolution, it's related with the mesh width that we use. So, thank you.
Thank you again. We can move to the next talk then.
Thank you.
Thank you, Ramiro. For the next talk, it's in remote. John Wilkin, I need your help, Marco, for this. John Wilkin, I will introduce John Wilkin when it will be online.
Yes, thanks.
Okay, so next talk from John Wilkin is about regional ocean modeling with data assimilation for improving mean dynamic topography and sea level variability forecasting in coastal ocean.
So
So can you hear me okay? I hope so.
Yes, perfectly.
All right. Sorry I can't be there in person. Coming to you from a secret location in Cadiz, in my hotel room. I'm terribly sorry if I've exposed anyone to COVID at the meeting. So here's a picture of me. That's what I look like when I'm well. I'm not going to turn my camera on. I'm going to talk today about some aspects of sea level in our data assimilation, our operational forecast system that we run for the East Coast United States. This is work by members of my ocean modeling group, Julia Levin, Eli Hunter, and Ian Anarango. And just a note, we are hiring. We're looking for a postdoc, so contact me if you find this talk interesting. So this is our region of interest. We've got a ROMS hydrodynamic model going here from Nova Scotia in the north down to Cape Hatteras in the south. The model configuration, I'll just run through very quickly. It's got a 7-kilometer grid, 40 vertical terrain following levels. On the boundary conditions, we use the Mercator Ocean forecast or analysis, depending on which we're doing, to which we've applied our own corrections for bias from a climatology, which I'll say more about. We had harmonic tides and the meteorological forcing is from the National Weather Service, high resolution weather forecast model. And we've got at the locations of these green triangles, we have daily inflow from gauges from the Geological Survey of the United States and Water Service Canada. So the domain is an interesting one dynamically. As we already saw with a little bit of background from Anne-Marie Bell's talk, there's a general southwestward flow through here. The Gulf Stream separates at Cape Hatteras, and between the Gulf Stream North Wall and the Continental Shelf, we get sort of permanent, well, in the long term mean recirculating slope sea gyre. It's really more the average of a sequence of Gulf Stream rings that drift through there, but that's the general sense to the circulation. And there's quite strong inflow on the Scotian Shelf. There's a recirculation around George's Bank, which is partly tidal rectification and partly buoyancy driven. It's a very well observed area, relatively speaking, for the coastal ocean. We have these regional observing systems in the United States, 11 of them. The Mid-Atlantic one covers from Cape Cod, here in the middle of the domain, to Cape Hatteras. We have repeat glider transects shown schematically here by this diagram. The black arrows in here are the surface velocity from a network of high-frequency radars, CODA systems. In the Gulf of Maine, there's a Nearacus observing system. Most significantly, the gray dots in here are a set of permanent telemetering moorings that give us velocity, temperature, and salinity data that we also assimilate. From 2015 until just a few months ago, the National Science Foundation had an array of 7 moorings here called Pioneer that we also assimilate into the real-time system. It's a very dynamic region because we have a lot of interaction between the slope sea and much colder waters on the shelf. And of course, we have the constellation of satellites to observe. And a rather unique part of this region is we have a lot of cooperation from the fishing fleet, and they deploy these sensors. You can see a little yellow pressure housing here. This is bolted on to the front gate of a fishing trawl. And we have observations of bottom temperature throughout this region over the last several years. We get maybe 30 or 40 observations of bottom temperature every day from participating ships in that. Just to put it all out there, so we've got both infrared and microwave. Satellite, polar orbiters and geostationary, all altimeters that are on. Any in situ observation that goes to the global communication, probably 1 or 2 per month, our regional observing systems, the moorings at Pioneer in the Gulf of Maine, and bottom temperatures from the fishing fleet. And every day we assimilate about 300,000 observations from satellite. So there's two main points I want to make in this talk. One is about, excuse me, losing my voice here. Let's hope I make it to the end. Is about mean dynamic topography. And what we have done is we started from the MDT that you can obtain from Aviso here. And we have improved upon that by running our own data assimilation analysis for a climatological model. So that means it's forced with climatological mean, river flow, surface stresses and heat fluxes, and we constrain that in a data assimilation with long-term mean observations. So in the top right here are long-term mean velocity observations. The little black dots are from our radar network. The blue dots are from permanent moorings. In the Gulf of Maine, there's been a long-term surface drifter program, which has been converted into a surface circulation climatology, and the orange dots are from a long-term program by the Woods Hole Oceanographic called Line W. So those are all velocity data that constrain the analysis. And just schematically shown over here on the left is a regional high-resolution climatology that we produced by a weighted least squares mapping. And along this line, following an isobath, 80-meter isobath on the shelf, you see the seasonal climatology. And just to emphasize, in July, August, September, in the summer, it's very strongly stratified. It's 25 degrees at the surface and 10 degrees at the bottom. So having bottom temperature observations is pretty important for this region. So when we do that, we get a much more dynamically and kinematically sensible mean dynamic topography. We've got the features offshore that are encompassed in Aviso, and we've got a more strongly resolved shelf slope gyre, and we tend to have contours of the mean dynamic topography following the coastline. I'll say more about that next. What we do is we use this climatology for temperature, salinity, velocity, and sea level to correct for biases in the open boundary conditions that we get from Mercator. And we use it as the MDT that we combine with sea level anomalies to get our total sea level, absolute dynamic topography for assimilation. So this is our climatological analysis, showing it again here. What we know from this implied circulation of the mean flow along the shelf here is that it should be balanced geostrophically by a pronounced across-shelf sea level gradient. And that shows up here nicely. Dynamical analyses have shown that the slope along the shelf, in order to be consistent with momentum balances and current meters, can only be about 10 to the minus 7 as a slope. So there shouldn't be any appreciable sea level slope parallel to the coast. Also, we should see nice contours of the geostrophic flow entering in the northeast. And in the Gulf of Maine, because of the deep basins that are there, there are gyre circulations set up, and those show up rather nicely there. So if we compare this to where we started with CLS13, you can see a large number of sea level contours going straight into the coast, which would imply geostrophic flow into the coast. And that's simply not plausible along the shelf. It's very shallow. It's predominantly well mixed on the inner shelf. And if you have a well mixed water column, any offshore Ekman transport, for example, in a surface Ekman layer can only be balanced by onshore flow in a bottom Ekman layer. It can't be balanced by geostrophic flow. So, and we don't see any of the organized inflow on the Scotian shelf or the gyre circulations in the Gulf of Maine. Moving forward to CLS18, which people can correct me if I'm wrong, but I believe this is what you get presently when you extract absolute geostrophic velocities from Aviso altimetry. We can see we're doing a lot better. We've got more of a front along the Mid-Atlantic Bight shelf break, a more intense slope sea gyre, the emergence of some recirculations in the Gulf of Maine, and some inflow from the Scotian shelf. But it's a very noisy MDT along the inner shelf, and not well organized in terms of what we would expect for the long-term mean flow. The CLS22 beta that I was given access to shows further improvements. a more realistic inflow to the Gulf of Maine here on the Scotian Shelf. But still, we now have more, although they're smoother and more coherent, we still have flow, geostrophic flow heading towards the coast and a very strong sea level slope in this sector that's not physical. So progress has been made, but for a broad continental shelf like this, the MDT is not usable for our purposes right up to the coast. So that's why we're working with our climatological analysis. So that's the story for is everybody hearing me okay, or am I breaking up?
It's fine.
Okay, all right. So that's the mean story. Now I want to say what we do for processing altimetry in order to use in the operational forecast system. Now in conventional mesoscale altimetry, the high frequency signals are removed by inverse barometer and DAC corrections, but those those dynamics are in the model. So we don't remove any of those corrections, and I don't like to call them corrections because you're actually removing physics. So there are adjustments to the data for particular purposes in mesoscale oceanography. One subtlety of what we do is we were concerned that small phase errors in the tide in our model, because it's low resolution for a tidal model, could dominate the model data misfit. So we do this funky business where we detide the altimetry, and then we add tide back in from the harmonics of a free run of our model. Then our hope is that the model observation misfit will be dominated by non-tidal dynamics, because we're trying to get that information into the model. The MDT, as I said, is the one that we've computed from our climatological 4D VAR. So we end up with observations and a model that should all be self-consistent with the open boundary conditions from Mercator, to which we have added in the sea level variability due to atmospheric pressure from the inverse barometer. And we therefore use altimeter data to within 10 kilometers of the coast. We subtract off a uniform value to bring the mean dynamic topography as close as possible to the regional sea level datum for this coast, which is the North American vertical datum, NAVD88, that the inundation people would be using for a storm surge. In data assimilation, it's a bit of an art, and it's all about the errors. You really want to have a realistic assessment of what your errors are. We assume plus or minus 4 centimeters for this is nadir altimetry. It's just regular 7 kilometer nadir altimetry. The time covariance. So in a gridded product like the Aviso optimally interpolated maps, they introduce an explicit time covariance function in their optimal interpolation. That is not presently an option in the way the ROM's 4D VAR observation operator works. So what we do to compensate is that we repeat the sea level observations for 3 hours, centered on the true observation time. And that pushes the solution towards something that's more dynamically plausible for us. If you just hit it with a single observation, the ROM's physics will come up with a perfectly reasonable physical solution, which is to generate a gravity wave that propagates at the square root of GH. And we don't want that. We want to get this information projected into the vertical with some baroclinic adjustment. And by repeating the observations for 3 hours, we make some progress on that. We have checked the validity of our observation and background model error assumptions using the method of de Rosier, 2005. I won't go into details. I have extra slides here if people are interested in this time. But there are metrics that where you can compare the observation error that you assume to the mismatch between the analysis and the original observations. And without going into details, you want these two ratios to be close to 1. That says that your assumed errors prior and posterior to performing the DA are self-consistent with your assumed errors in the models. So we do have values near 1. If you think 1.3 is close to 1 and 0.75 is close to 1, we're okay with that. And importantly, the residuals, which is how well you fit the data after assimilation, compared to the innovations, which was the misfit before assimilation, you want that to be less than 1. That means you've actually reduced the errors. And we're down here around 0.29. So I'm very happy about that. This is all described in more detail in a paper that came out in Progress in Oceanography. And if you zap that QR code, it'll take you to that paper. So how well did we do? So what I'm showing here, left to right in best to worst model, we've got bias, correlation, and RMS errors. And here, light shades are good, RMS error low, and a correlation high. So we've got good correlations out here offshore, less good against the shelf, but better than Mercator, and a lot better than Goff's, and a lot better than our own model if we don't assimilate any data. Similar story in the RMS errors. And interesting story offshore. I thought that these relatively high RMS errors near our open boundary were an open boundary effect, but you look at things for Mercator, which is global, and Goff's, they also have errors. They don't have an open boundary out here. So this must be something to do with not really representing Gulf Stream variability as well as we would like. Now, looking at, and this might be interesting to Andres following his talk we had in the previous session, just focus on the plots on the left. These are frequency domain coherence. So how well do the wiggles match up in time at all different frequencies? And therefore a set of tide gauges that are marked with the little red dots in the map in the top right. Eastport and Portland are in the Gulf of Maine. And we have very good coherence at high frequencies, both in the non-assimilative model in the red and the assimilative model in blue. And I put that down to being a well-configured model with good local forcing. And you see that Mercator is not doing particularly well in those frequencies. And it's not until these longer timescales that it's really approaching the skill of our data assimilative system. Similarly for Portland, and now as we come around Cape Cod and into the Mid-Atlantic Bight, those global models are doing rather better. Mercator is always doing better than Goff's, and our assimilative system is always at all frequencies doing better than anything else. So I put this down to the role of assimilating altimeter data all the way into the coast. So we tried to put that a little bit to the test. So running a couple of years where we did not assimilate the coastal sea level. So here we excluded our altimetry inside the 500-meter isobath. And in the Gulf of Maine, you can see there's a consistent offset. The coherence drops when the coastal altimetry data is not assimilated. It doesn't really affect the high frequencies. In the Gulf, in the Mid-Atlantic Bight, there's really not terribly much difference. But of course, the sea level is being assimilated up to 500 meters, and we're rerunning another experiment now where we don't assimilate any altimeter data, and I think it's just going to be a disaster, but that remains to be proven. Just a few other results. I've got just a couple of minutes. We've done all sorts of assessments of the model over a long 15-year analysis. And here are just a few results looking at what we've done in seasonal cycles so that we can look at interannual and mesoscale variability. So what we're seeing is anomaly of the bottom temperature in the Gulf of Maine. And you can see in our model, we've captured those observations very well. And I just mentioned this because when you look at the signal over 18 years, it goes from all blue to all red. So there's a very dramatic warming of over 1 degree per decade in the bottom waters of the Gulf of Maine, which is wreaking havoc with the ground fisheries and the lobster population in that area. Just a word on these bottom temperature observations from the fishing fleet. In an analysis where we did not
2 minutes.
Okay.
2 minutes.
Where we did not assimilate those, we've got we still have a much better fit than these other models. And now we are using those in the real-time system. So those analysis fields that I showed are in output. You can go to, you can search my name, it's Cino, and you'll find this analysis. All of the data every hour on the model grid is there for 15 years if you want to do something with it. And we have an observation control panel that we use to monitor the system. We track every observation by its provenance code. So each altimeter by whether it's JSON, TOPIX, MVSAT. We can look at what was the model data misfit before assimilation here in centimeters. What was it after assimilation? We've got a much better fit to those data. So in summary, we've got an operational system that downscales a global model, assimilates local data, and improves on all of those. We're using 1 Hertz nadir altimetry, but by improving our dynamic topography, we can take those all the way into the coast. While the CLS MDT has improved dramatically, it's still somewhat unphysical on parts of the shelf. As I said, the data assimilation significantly improves performance in the mesoscale, which I attribute to the assimilation of altimetry. And that's it. We're hiring. Go to jobs.rutgers.edu and search for us.
Thank you, John. Any questions for John? Okay.
Hi, John. This is Angelica. Right when you were discussing the elevated RMSC over the shelf, sort of near the open boundary of your domain, you were cutting out, and I was really curious why you thought that was so high in that area. If you could maybe go over that again, I'd appreciate it.
Yeah, I think I would anticipate that for my model, it's a poor representation of the Gulf Stream so close to the open boundary. But neither Goffs nor Mercator do a good job either, and they're global, so it's not an open boundary effect. So I'm at a bit of loss for that. I think if we extended our domain, we would be able to constrain it because we're potentially making greater use of the altimeter data. But I don't have a good reason why Goffs and Mercator are so poor.
Hi, John. This is Paolo Cipollini. Thanks very much for your talk. If you can cast a quick comment on how this is going to evolve in the future. I see you're using RADS for consistency 1 Hertz, which is great. But do you think this will evolve to use higher frequency, higher rate data? What do you think? Thank you.
We do have a NASA OSTST project to look at that. Something we found, and there's a set of papers in ocean modeling came out over the last 2 years with Julia Levin as the first author, where we've done some nested data assimilation in the region of that Pioneer array. We nested 800 meters, and we were simulating observations. So what that we have is shown here with this high-resolution model. Now, what we found, short story, with the model, the emergence of a much stronger.
John, we have some trouble to hear you now.
Of direct velocity observations. Scale
okay.
in the Pioneer could be used.
We have some trouble to hear
I'll
you.
send you an email, Paolo.
Okay, I propose you answer again to Paolo, but maybe offline because we have some troubles with the sound now. Okay, and I think we have to move on next talk. Thank you again, John.
All right. Our next 2 speakers are coming from German Geodetic Research Institute, DGFI. And the first of them is Julius Ulesman, who is going to talk about coherent modes of coastal sea level variability from altimetry and tide gauge observations.
Hi, everyone. So, yeah, thanks for introducing me. I think one of the main ongoing questions is how coastal sea level variations differ from the open ocean. And there are many studies, of course, that have shown that sea level at the coast can be highly decoupled from the open ocean. And of course, understanding why this is happening and to what extent coastal and open ocean sea level differs is very important, not only when we think of validating tide gauges, for example, so what are the regions where sea level is consistent and coherent, but also from a mechanistic perspective, because we would also like to understand the drivers which cause such coherent sea level variations. And that sea level is indeed strongly coherent on the continental shelf is shown in this plot where I simply show correlations computed on a long track data with respect to the coastal data. So coastal data is here defined as the average in the first 10 kilometers to the coast. And we see that the 1,000 meter isopath strongly divides or kind of is highly correlated with the decay scale of these correlations. Also, we know that sea level can be strongly correlated along the shelf, and that has also been shown by several studies almost 2 decades ago. That can be due to the influence of large-scale forcing, like ENSO or climate variability, and these alongshore correlations can be as long as tens of thousands of kilometers and establish such correlated pattern. However, we think it's not really yet systematically explored and identified how these correlation pattern are defined and what the across and alongshore correlation scales are. So we like to explore this in this work, and we use also coastal sea level products which are well suited to discover this. So first of all, we wanted to understand if we could kind of cluster the coastal sea level variations into regions which share a lot of variability. And to answer this, we used tide gauges from PSMSL and applied a clustering approach, which is in this case Bayesian mixture models. You could probably also apply other clustering approaches, but with this approach, we can nicely also estimate all the uncertainties associated with that. And here we associated these observations called y, which are given at a location n and time t, with a function which contains a set of autocorrelated time series. Here they are modeled as second-order autoregressive processes, and we prescribed also the number of clusters, and then we estimated a categorical parameter k, which defines what tide gauge is linked to which cluster. And also Fune in a one-dimensional way, such Bayesian mixture models can be also Fune in a one-dimensional way on the right-hand side, where the set of observations can be associated with a mixture of different Gaussian distributions. This is our result. So we could show that they are actually regionally coherent clusters, which also look pretty meaningful considering previous research. So we see a strong connection and sea level variations along the northwestern US coast or the North American coastline. And then we see some division in sea level variations in the Gulf of Mexico and Florida regions from the northeastern US shelf region, and also some other pattern have been previously described, like Baltic Sea, that this moves very coherently, and also these strong connections of sea level variations in the Mediterranean Sea and along the Western European shelf. So these are really interesting features we found here. Also, when we look at the correlations of these cluster time series with the tide gauges, we found that already explain a lot of fraction of the coastal variance with just these 12 different time series. And it's usually in the order of 0.8, and 60% variance is explained with this approach. Of course, there are some outliers, but that's mainly because some of these tide gauges cannot be clearly associated with a cluster because there's just very, very few tide gauges in some regions. Also, when we look at the time series, we see strong differences in terms of the variability and spectral properties, but in this, what we have looked at so far, we don't try yet to explain or make any assumption about the drivers or computer sea level budget or something like that. But we believe that this can motivate future studies while trying to close the sea level budget at such a scale. Now, what is really interesting, how these clusters look in space, and to show this, we used coastal sea level data here, used monthly averaged data from the JSON missions featuring coastal retracking, and simply show here correlations of these cluster time series with tide gauges and, well, the altimetry data. And again, as in the first plot, we see that these structures are really confined to the continental shelf and also differ depending where you are. For example, in closer to the tropics, these features get much larger, and there's you lose this dependency on water depth, but that's of course also caused by large-scale barotropic processes. Now we can also look at these other clusters and pattern, which have also already been described in other studies, and a lot of their variability can also be explained by, for example, the NAO or ENSO in the northwestern US coast, for example, or PDO. Now, what might be interesting is to understand how these cross-shore correlation length scales and how the alongshore correlation length scales actually behave. So we try to quantify this, which is of course also important when it comes to because it gives a good indication of what length scale do we actually need to resolve with products like gridded altimetry, for example. And again, I showed a slide from the first plot, and based on this analysis, I computed cross-shore correlation length scales simply by fitting these correlations on the track to an exponential decay function. And this decay factor lambda gives us this decay scale. And in the bottom plots, I plotted these cross-shore decay scales. On the left, that is based on altimetry versus tide gauge observations, and on the right, it's altimetry versus altimetry only, and we use here like a virtual station approach. You see in the upper right plot that there's kind of a dependency on latitude, but with a very high local and regional variability. That can also be visualized when we look at the plus minus 1 standard deviation margins. And also when we compare this, for example, to the first Rossby of deformation, we see a strong proportionality, which indicates that coastal processes really kind of set length scales of these coastal variations in the cross-shore direction. Of course, there are regional differences and outliers. For example, in the Baltic Sea, these length scales are much larger, so it's not a high correlation with the baroclinic Rossby. Why is this interesting? It might, for example, be interesting if we want to understand how well gridded products actually resolve coastal processes. And here in the blue line, I plotted a correlation length scale which was applied in previous gridded products. That's kind of the zonal smoothing length scale. And when we it's clear that some of these cases, this length scale is way too smooth than the actual length scale of the causal processes. And here we can also see the differences of the actually observed length scales and this smoothing length scale. And in many cases, gridded products would need to be much higher resolved to resolve such processes. Now, my final slide, I would also like to show the longshore correlation length scales, which are computed on a very in the same kind of way. I skip these single examples here for now. And here you have to choose a direction, so along which direction you look at the coastline. And it shows here an anticyclonic direction indicated in the upper left plot, because that's actually against the direction of propagation of causally trapped waves. So in this way, we would see sea level which would already be affected by any causally trapped waves originating from that direction. What we found is that these alongshore correlation length scales can be very large, up to tens of thousands of kilometers. And there also seems to be a dependency on whether you're at the western or eastern boundary. But we're not yet conclusive what might cause such effects. But if you look in the other direction, so if you look in the same direction as the propagation direction of Kelvin waves, you see in some areas like the Eastern Indian Ocean or the Eastern Pacific, much decreased alongshore correlation length scales. So that's for us an indication that such processes like causally trapped waves might influence such pattern. So to sum up our findings, we could show that coastal sea level variability can be highly coherent, and we can cluster some regions such that a few clusters explain already a lot of the coastal sea level variability, and that could motivate future work trying to better understand the sea level variations. Also, we see that the across-shore correlation length scales is often highly correlated with the shelf width, but that's of course not always the case, as can be seen in this example, which I skipped, where we see the correlations plotted against distance to coast and water depth for different locations, and we see it's not a universal relationship, so like stratification or other local characteristics might be very important as well. And overall, of course, gridded products cannot resolve these across-shore correlation length scales, so maybe that's also a motivation for new gridding strategies. And yeah, with this, I'd like to close this talk, and I hope you have a lot of ideas and comments. Thank you.
Excellent timing, Julius. Any questions from the audience? We have 5 minutes.
Yeah, nice talk. It's really interesting. Yeah, Bayesian methods are great because of what you said. You can quantify the uncertainties, but show them. So did you look at how stable these clusters are? And that's sort of with an eye to the time scale too. I mean, there's been work that showed that correlation across the East Coast, across Hatteras, is dependent on 20, 30-year time scales and kind of flips throughout the 20th century. So.
Sorry, you mean it flips like the pattern, or?
Yeah, so that correlation, that cluster, if you look over different time scales, will change. Okay, yeah. So
yeah.
Clusters?
Yeah, okay. Yeah, so concerning like the time scale dependency, so that's for sure very interesting, how it looks at low frequencies. I mean, this is monthly data, might change. we tried it with annual data as well. So this is monthly data. So might be something we're gonna investigate. And in terms of uncertainty, so some of this is of course also still preliminary work. Of course. But the uncertainties of the time series themselves are actually plotted already here. It's really hard to see. So they're very, very, very low. Yeah, so it might be that this is really just the uncertainty of the model time series, and we don't show yet like another hyperparameter like the standard deviation, which is also a parameter we model explicitly. But they seem to be very robust. But I also plan to show the individual tight gauge time series next to these plots, then you might see better like the spread tight gauge time series.
Thanks.
Just a curiosity. So thanks for the talk. Just a curiosity about this time series. Why are they all flat?
There's no trend in sea level. It's the trended and the season data.
Okay. Okay. But when you did the clustering, you didn't remove the average of each time series.
Yeah, it's all the mean is subtracted as well.
So why are the time series? So is that they are artificially aligned over 4 meters of for the plot, or?
Yeah, it's for the plot. Yes. Yeah.
I think my question is related to the coherence for the north. Okay. So for the Northeast Pacific coast, Northeast Pacific,
yes,
and just use the previous slide.
Previous?
Yeah. So seems you can see it's very red from at mid latitude and high. And so southern part is nothing there. So can you explain, do you have any reason or any explanation why it's so highly coherent in the northern part?
Of the Pacific?
Yeah, Northeast Pacific. So basically from like Oregon coast or Washington coast to Canada coast to Alaska, right? So see, it's very highly coherent. You mentioned also, I think, Pacific Decadal Oscillation. But could be that part be actually related to ocean gyre, the gyre circulation of so if it's related to PDO, it's related to ENSO, I would expect maybe the coherence would be strong enough, like from like California coast and northward to Canadian coast and to Alaska.
So I don't know why this is so coherent. It's related to the PDO, so like there's some correlation, but also but that's maybe also correlated with each other. So I don't know the actual mechanism causing this, but I think it is often argued as the response of positive trapped waves really establishing such long correlation length scales. But I can't prove it. But I think it's worth to investigate.
Okay, thank you.
Any more questions? No? All right, thank you, Julian. Before I invite our next speaker, I would first like to ask if Saulo Soares and CK Shum are in the room. Okay, can you please quickly upload your presentations?
System. That's fine. It's your turn. Is turn now to speak? No? Okay, because he provided a pen drive for Mac, and so I cannot upload the presentation. So we'll manage it in some way. Yeah.
I can't believe Bill Gates.
Really? That's fast. Okay, so who's presenting now?
Okay, our next speaker is Marie-Christine Yulf with her presentation about wind as a driver of subannual sea level anomalies on South Brazil and Patagonian shelf.
Thank you, Nadia. Hello, everybody. So I will present today wind as a driver of subannual sea level anomalies on the South Brazil and Patagonian shelf. This work is part of the CIRCOS project that I am currently working on as a PhD student at DGFI TUM. And so CIRCOS aims for a better representation of the shelf and coastal circulation. And we don't want to only use altimetry, we also want to combine this and use also wind data. So this is why this study is the first step of going there. So this is a little application study of the gridded current altimetry data and how the wind is impacting the sea level anomalies. And at the end, I will give you a little outlook, what we will and what we could do with this information we gained. So first of all, welcome back at the southern western Atlantic continental shelf after the talk of Laura in the morning. Yeah, we are on the largest continental shelf in the southern hemisphere. And when you look at the figure, so here we have a nice figure of bathymetry, we see we have a very diverse study area. So we have in the north a really narrow shelf, while in the south it is pretty wide, really wide shelf. We also have very special dynamics. So here you see, for example, we have two main currents. So the Brazil current is bringing warm water from the north, and Malvinas current, which brings cold water directly actually from the ACC. They both meet, and this is called the Malvinas-Brazil confluence. This is actually also something we saw before in the ESA-2 talk, if you remember. It's known to be a very dynamic area, yeah, with also a lot of turbulences, of course, and this also influenced the shelf. And we also have influence of rivers, of course. Here there is one. Let me show you here. One really large river, the Rio de la Plata, which also influences the shelf, of course. So previous studies on parts on the shelf showed already that wind is an important driver of sea level anomalies on parts of the shelf. And those studies mainly focused on the annual scale. For coastal and shelf regions, of course, the shorter temporal time scales get more important. And thus, the objectives of the study were to answer the following questions. Is the high-frequency sea level anomaly variability driven by the wind? And if so, in which frequencies and in which regions? And also, we want to gain more knowledge about the gridded altimetry product. To what extent can gridded altimetry reveal this high-frequency sea level anomalies on the shelf? So in the end, I will hopefully answer the questions. The data that I used are the sea level anomalies from the gridded products on level 4, and also a numerical model run, both from Siemens. So the model is based on the Mercator model. I used daily resolution data, and both are used on the 0.25 degree grid. And the nice thing is I could really use a long time series for this data, so from 1993 to 2019. And I also made use of the derived geostrophic velocities that are associated with the gridded altimetry product. The wind speed components that I used are also in level 4. They are mainly from spectrometers. It's a merged and gridded product as well. It's actually in a 6-hourly resolution, but of course I used a daily averaged version. And I also modified the wind components into the alongshore and the cross-shore component because this is more relevant and you see better the processes. And in the following, we will focus on the alongshore component, which is the wind speed parallel to the coast. So this study is based on the magnitude squared coherence. We saw some people using coherence before, so this is very nice because we obtain a correlation, but moreover we get a correlation per frequency, so we can see how well two time series agree, not only on time but also frequency, and also frequency bands, and this is what we will do. EOF analysis also, I will also show you some results of that. But let's go straight to the results. So I show you here the coherence between sea level anomaly and the alongshore wind component. And we start with the lower frequencies that are analyzed. So we go from 100-day to annual periods. And at the top row, you see the results coming from the altimetry sea level anomaly. And in the bottom row, the model sea level anomaly. So when we look at this picture, of course, we first see there is a very large, very high coherence at the annual scale. Yeah, the highest coherence is found at the annual scale, and this fits perfectly what previous studies showed at some parts of the shelf. And we also see that model and altimetry agree in this sense here very well. So we have the same spatial coverage. Also, this study provides a little bit more because we now see the whole extent of this annually driven, wind-driven sea level anomalies. So we really see like the whole shelf width is covered, and above 50 degrees south, we have this impact. When we go to higher frequencies, so more to the left, we see that the coherences are more restricted towards the coast. We see currents like also getting lower and like I said, more at the coast, and also that we got more pronounced coherences here at the Uruguayan and Brazilian coast. And we already see when we look at the periods from 100-day to 175 that we find a better agreement of wind and sea level anomalies for the model, for the model data. Going to higher frequencies, because that was what I was really interested in. Of course, we don't obtain that much coherence as we saw before at the annual frequency. We now look at 20 days to 100 days. And even if the coherences are much lower, we still get significant coherence of wind and sea level anomalies for all of the periods. So that means that the values are above 0.3. So everything that is yellowish is significant, and we get this for both of the products. But it's really notable that we obtain more wind-driven sea level anomalies for the model, and this gets especially here very visible. So here we have barely a signal or agreement in the for the altimetry sea level anomaly, but with the model we have almost like the whole coastline covered. And yeah, again, notably, Uruguayan and Brazilian coast is wind-driven. So as I said, I also made use of the geostrophic velocities, and I made this comparison in the same way. And here you see the coherence again of the alongshore geostrophic velocity that is associated with the gridded product and the alongshore wind. So why we are doing this? So now we can not only see where the wind drives the anomalies, but we also can see where the wind drives the shelf circulation. And why are we comparing the alongshore component with the alongshore component? That has the following reason. So the alongshore wind drives, after the wind circulation theorem, in a cross-shore ocean mass transport. And this results in a pressure gradient and causes geostrophic velocities or enhances geostrophic velocities. And yeah, we see that in parts of the shelf, we have really circulation driven by the wind through geostrophic adjustment here. And it's again at the Brazilian coast very prominent. And we also see some features. We see here an interruption in the wind-driven circulation. At the annual scale, so there's really like and this I would suggest that this might be connected to the influence of the Rio de la Plata, so the river discharge. It's really known that this river is influencing shelf circulation a lot, or it could be also connected to the Brazil-Malvinas confluence. We also want to know like how much variability is actually driven by the wind, so below the annual scale. So we also applied an EOF analysis. So where most of you probably know it. So with an EOF analysis, we decompose the sea level anomalies into modes of variability that, and we compared those modes of sea level anomalies coming from those modes with the alongshore wind again. And we found agreement of the alongshore wind in the second EOF mode. And this mode describes 10% of the variability on this whole shown shelf and showed an agreement of 0.6. So you can see a snippet from a time series in B. And also we can see the coverage of this agreement on the map. So we see that we get a very good agreement of both of them, so of the second year of sea level anomalies and wind of the station Mar del Plata. And at this point, we also see that they both match and the frequency at 70 days the best. So we get a very good peak at 70 days. So when we look again into the comparison of the model and the grid altimetry, we see here their agreement above 20 days. Yeah, in the south, it's like we would expect it. So at the coast, we have, of course, a lower agreement. In the mid-shelf, we have the highest agreement. It's a little bit different in the north. So we have a high agreement at the coast and a lower at the shelf break. Below 20 days, there is no agreement because the resolution is not sufficient enough. And when we look into the energy perspective, we can see at the point A and B, above a month, we get a quite good agreement of the model and the altimetry. And below, the energy of the altimetry product drops or is lower and drops at a few days. So to give you the full picture, we also have to talk about things below 20 days because nice things are happening there. So this is the coherence of wind and sea level anomalies for the model, for the sea level anomalies coming from the model, because they actually show a good agreement along the whole coast. And something that I wanted to say here is, of course, this is not catched by gridded altimetry, so this is not was not possible to make with this gridded product. But it shows that the wind-driven sea level anomalies are really necessary to observe the coastline shelf processes. So yeah, this would, of course, maybe open a discussion or that you think about the correlations, of course, we apply, but not only the correlations are, of course, causing this. It's also about the interpolation we apply. And it would be really nice to yeah, see more, like below 20 days, of course. So to answer the questions from the beginning, yes, we have wind-driven sea level anomalies in all frequency bands, so above 20 days for the gridded altimetry. And they are most notable along the Brazilian and Uruguayan coast, and of course dominating annually. The coherence of the wind is notably higher for the model than for the altimetry for 20 to 100 days. And the wind-driven variability below 20 days is fully suppressed by the gridded altimetry. Yeah, but I don't want to leave you with this as a last slide. I also want to tell you what we could use this knowledge for. So here's a suggestion for me. We could use this information of high frequency wind and their correlation for the gridding, for example. And yeah, so here I have a preprint that Marcello and I just published in Ocean Dynamics, a paper about the machine learning gridding process, and such an approach would be feasible to also use other data such as the wind, and this might lead then to a better representation of the shelf circulation. Yeah. Thank you.
Marie, thank you for the great presentation. Do we have any questions?
What's the width of the typical width of the continental shelf there?
Sorry, can you?
What's the typical width of how large is the continental shelf that region?
Yeah, that's a good question. I'm really bad with such numbers. I can tell you right now.
All that is continental shelf.
Does it help? Oh, we have an expert.
I can give you a hint. At the south latitude, you can have a width of 800 kilometers, and in the north, around 3 100 kilometers or 200.
Oh, so it's quite bad.
Yes.
Thank you, Laura.
Actually, I have one. For your SLA, what correction do you apply? Inverse barometer or a dynamic atmospheric correction? Because if you are studying coherence with wind, this could impact your results. So
Yeah, so impressions if I apply for
if you applied, and which one?
So it is applied by default. So what you can do is you can only like take it from on the L3 level, so on the Altimetry, and interpolate it. But there's no like a DAC for L4. So it's applied here. But you can also remove it. Like I said, you can manipulate it and remove it. But I guess, so what I was a little afraid of, that you add an artificial signal, let's say, when you like remove a wind-driven signal. Yeah. So here it's applied, and that's also one of the reasons, of course. Yeah.
Thank you.
Thank you.
So if there are no other questions, we can move on to the next talk, given by Saulo Soares for coastal to open ocean exchange processes in the California current system from Altimetry, ADCP, and HF radar data.
Okay, good afternoon, everybody. So I'm Saulo. I'll talk about this project I've been working on with Sarah and Terry. There are scripts with help from Marcello. And so the previous talks talk about very, large things and low frequency processes. We're gonna actually now look at small scales. So our idea was essentially to try to get a sound physics-based methodology to try to extract cross-shore velocities and eventually get at other more interesting things like fluxes of heat and carbon using high-resolution altimetry. And with the underlying idea that in most coastal settings, there is actually a large role played by eddies, meso and sub-mesoscale eddies, which I loosely call sub-mesoscale here, anything that's basically less than 100 kilometer wavelength. They're geostrophic, and I think it's possible to do from altimetry. And we will start in the coast of California because it's an upwelling system, so lots of carbon comes up, needs to get exported offshore. And, this regime is very short, narrow shelf, underlied by a very eddy-rich ocean. So, if we couldn't get it done here, we probably wouldn't work elsewhere. And obviously, it's very highly sampled by in-situ data and these sort of coastal radars that Sung Young talked about earlier in the morning. Now, here is to show you an example of how much what happens way offshore can have a meaningful impact in the coastal ocean. So in this case, in 2020, there was a large cyclonic eddy that developed offshore Point Conception, that little point there. And it basically advected all these recently upwelled water, and it does so via this very narrow filaments that are about tens of kilometers wide at most. It so happens that we had crews out there shortly after, sort of around the peak eddy, where we made a repeated intense survey of it using underway CTD. So we kind of mapped the eddy and the inside sub-mesoscale structure, the filaments. So what you will see here is an example of the sort of this data collected here, coming from south to north, and you will see things like fronts their subsurface signature. All these wiggles are internal waves, and we get also near surface trapped features, which we think are very important for these processes. And what's the role of altimetry in this? So we started thinking about dynamic height that we could estimate from that data, and that are basically the dynamic heights we got from the underway data. And down here, it's comparing that same track here, which is roughly aligned with the JSON, one of the JSON tracks. And this is basically to illustrate the sort of difficulty that we have, because our measurements are indicating that all that fine structure of the ocean has a very small, centimeter size scale, and most of the time what you will get out of an altimeter is a lot of high frequency variability. And for our purposes, it's not just a noise, sort of like an instrument noise, it's also there's ocean processes that the altimeter sees that we actually do not want. So all sort of non-geostrophic processes are noise to us. And so the idea is to leverage observations, mostly just observations, no model for this. So we have here the coastal radar network, the coverage offshore, and then we have lots of historical cruises which have ADCPs mounted on them and give velocities. And we want to start leveraging them together with the various altimeters. So just to situate ourselves, we need to first know what if our measurements are going to be able to do it. So to do that, we first thing are basically comparing what we can know about these small scale structures from the cruise versus what we would statistically derive from an altimeter, like the JSONs and now some of it included the Sentinel-6. So they are plotted in spectra form here. There's the two altimeters, some with they use the AOS, in the case for the JSON. And this line here is basically our in situ observations of the steric height. And the key thing to know is that as soon as you leave the sort of 100 kilometer scales, the observations are indicating that the height power is plummeting, going well below the noise floor by about 60 kilometer scale. So it's a very it's a region of really unfavorable signal to noise. Close, but probably unfavorable. And this has been a theme as we've worked on this a bit, that no matter exactly what product you're using and looking at the various processings you do with it, the sort of mismatch that occurs right around this area here, not just on the power magnitude level, but the behavior of the spectral characteristics, often showing a lot of this sort of change in the slope of the spectrum. It's kind of important to us as it signals quite a bit of the influence of noise in where we kind of want to make improvements towards. And so we want to try to recover more around this area. And we are also concerned that sometimes with these types of measurements that we can do, we can't profile very deep, and also we don't go as fast as a satellite with ships, so maybe we're missing some more internal variability. And one big process is something like an internal tide. And in here, we're trying to leverage this sort of long time series that we get off there with the coastal radars. Sung Young already talked about this type of product further up north. It's really useful. It has been shown in the past that you could derive sea surface height out of the currents under certain conditions. And it's quite promising, as you can see here, that was 10 years ago, and it looks pretty good, although there are important differences that we want to understand better.
And partially that comes from once you're trying to invert the height from currents, your currents are not, you want really purely geostrophic motions, but you have processes like inertial oscillations, which are pure rotational currents that don't have height signatures that will contaminate your potential signals. And then you have all this array of examples of unbalanced phenomena, but these not only have signatures on currents, but they also have in height, so kind of a double problem. There will be somehow in the altimeter measurement. We start by trying to understand these processes a bit better by looking at something like a frequency wave number spectrum. So this is wave number, so spatial scales computed inside this domain here offshore. And this is frequency. Here is the semi-diurnal tide, the inertial peak, and the diurnal or near diurnal tidal constituents. And this is the kinetic energy. And we want to use something like a Helmholtz decomposition that, again, Sung-Young talk a bit about it, but it's a way to sort of partition these two types of, vector motions that are measured by the radar. So here is sort of the divergent power you would get by applying this Helmholtz decomposition to the current maps. This is the rotational part, or sometimes called solenoidal. And it basically the geostrophic signal will be in here. This is stuff we ideally wouldn't want, but contains a lot of information of the unbalanced part. And so we want to think about ways to extract things out of here that are very useful, maybe messages. And one thing, if we collapse that three-dimensional into just frequency here, you see, so this is now basically the frequency content of those sort of smaller scales, sub 100 kilometer there within those boxes. And you see that actually, even at low frequencies, like lower than the inertial frequency, you still have quite a lot of divergent motion. So basically just a pure filter in time wouldn't work to get good geostrophic currents out of it. And also shows quite strong this sort of the standing tide. It's not really propagating anymore, the diurnal one. And then you have this semi-diurnal one here. That's our main concern in interpreting those in situ measurements, whether we are capturing that or not. And we can try that by looking at how much it actually contributes to the then spatial variance, so the wave number, which is similar to what we would observe, but this is still in current form. So in terms of the currents components, we're finding that this semi-diurnal tide only contributes to about 15%, which I'll show you why it's relevant, irrelevant. Yeah, before, another concern is that the radar measurements they're great. They got this great coverage. They have access to time, but they are nowhere near as a precise measurement as things coming from ADCPs. So we've made some prior effort recovering ADCP data of the area, so that we can know how the currents behave at very small resolutions. That it's also something that radars typically don't do. They're capped by the mapping procedure, not unlike the procedure for mapping altimeter that really degrades the scales it resolves. But that's not a limitation of ADCP currents. We're able to use that information along with more assumptions to do a similar type of Helmholtz analysis, and we obtain estimates for rotational and divergent components, and find that qualitatively they agree quite well with very nearly similar power in small scales between the two components. And we've done this for older data and newer data, and we typically find very consistent history of this. So we think that the radars measure it, we have the correct picture. And if we expand from offshore to inshore, as far as we can tell, these main messages don't really change too much. We're still seeing lots of low frequency divergence, the predominance of the semi-diurnal tide. In fact, we're thinking we're getting modest increase in the contribution of the internal, I'm not really sure how internal it really is at that point, but so that component really starts contributing a bit more and then decrease in the inertial, much similar to the conclusions from this morning. And so that's reaching the end of what I wanted to say. And I was mentioning this, then basically this divergence at right outside of the 100 meter wavelength, kilometer wavelength, where the observation seems to diverge. And, with possibly the influence of this sort of white plateau noise, which I don't quite understand exactly what's the source of it, what the various contributions that we can, that leads to it. What we know is that we can estimate some processes from either directly in situ measurements or inference from the radar. And we don't think we're missing a big signal that would be problematic, like the internal tide. As far as we can estimate its signature based on the kinetic energy in the radar, this is where it would sit at a very conservative type of estimate, considering that all that energy and that motion concerns a very large internal wave. It's probably not the case. It's spread into many other sort of vertical modes, but that it's still really low. And so we either measure most of it, or if we're missing something, it wouldn't explain none of the sort of disagreements near the almost resolved scale. So it's not really too big of a concern as far as extracting that signature, but we're thinking that maybe some of this is some form of noise that comes from the other very large ocean process that's at much higher frequency, which are surface gravity waves. These are measurements from lidars flown just north of our site, maybe actually maybe a year after or so. And the statistics of it, it's quite similar for where we have the same overlap region, very low power, a very steep drop off that's sort of diverging quite fast from altimeters, even where you would think altimeters should still be pretty good. And yeah, but right after it, there's very large, complicated sea state processes that perhaps we don't know yet how we could use that to remove and improve our estimates here. For the future work, we'll try to use the radar to invert some sea surface height and kind of understand better what are the signals here and the differences to what the measured altimeter is, and hopefully try to get a better sense of if there's something that it's tied to surface gravity waves, missampling. And although this is based slightly offshore, we think this is quite relevant because as we're going to approach the coast, we expect a modest increase in the issues coming from the imbalance, the internal tides, but a much larger difficult to dealing with the gravity, surface gravity wave field getting, or reorganized in a different scale. Yeah, I'm done. Thank you.
Any questions for someone?
Yeah, I have a question for you, but maybe for Sonia and Lotfi. When the internal waves come in near shore, I guess the wavelength gets narrower, and then we have surface wave near shore where also the wavelength get narrower. And do people looking at waves like surface wave heights should worry about the component that would be a contribution from the internal tide? Or is it two different levels?
No, yeah, there is research showing that there's effects of all sub-mesoscale processes affecting current, either the current field divergence or rotational, both impact the gravity wave behavior. So they modulate basically the behavior of the surface waves, and then probably organizes them kind of in that two-way interaction that it's maybe becomes very challenging to would be basically the first order easiest analysis to try to infer for example, the magnitude of the internal wave signature, but we probably cannot deal with that problem of the interaction, at least so far with what we know present.
Other questions? If not, I propose we move on for the timing. Thank you. Sorry? If not, I propose we move on because of the timing. Thank you again for this presentation. Do you want to introduce me? Okay. And I introduce our last presenter of this session, C.K. Shum, with the presentation for joint estimates of coastal sea level trend and vertical land motion in the northern Gulf of Mexico.
Thank you. Thank you. So this is some work ongoing, and the title actually, the content of the presentation actually changed a little bit. So it's joint estimate of coastal sea level trend and vertical motion, and I put down northern Gulf of Mexico. At the time, it was of a lot of interest to us, but we extended the study a little bit to almost globally, and this is work in progress. So my student Shen-Dao Wang and Chong-Yan Kuo is a national Cheng Kung University in Taiwan, and also Wen Hao Lan in National Taiwan Ocean University. So I don't have a list, sort of a talk, but I just want to show you this sort of complicated flow chart. So this is an algorithm circa a former student published his dissertation in 2015-16. So the idea is that the vertical motion of tide gauges, even with the global tide gauge global GPS at tide gauge network, a lot of times do not measure the same motion. So we there's a long study starting 2004 by Chong-Yan Kuo et al., where we actually do a network adjustment, try to estimate for vertical motion at tide gauge location, because tide gauges usually the motion is follow, you put the tide gauge on a pier usually, and you have a benchmark off-site. However, the benchmark, you have to survey it from time to time. A lot of times they will not survey. So you're talking about very different motions. So the idea over here is that this is, by the way, a pretty, maybe not totally irrelevant flow chart because we added a lot of more information, and I can show you on the right-hand side, these are the formulas. And I should be the first to say that we're not doing acceleration in this talk, but obviously instrument correction acceleration could be also put in. So this is more like generalized talk of our wish list in the end. So this is a progress report. So the idea is that we wanted to do a sea level reconstruction. I didn't bother to try to explain what a sea level construction is. Primarily, it started from Church and White in 2006 publication, and then they followed with 2011. And there are many others working on this sea level reconstruction, meaning that they wanted to take satellite altimetry, very high spatial resolution, but they are short at the temporal resolution, for example. But tide gauge, global tide gauges, they have a rich spectrum of sea level, but only at a point. So the idea is try to combine the two measurements. So this is sort of like art and so on, and many controversy and debate. But now that we reached 30 years of satellite altimetry, so actually almost 40 years, 30 years. So therefore, so we just revamped this method. So what I wanted to do, let's see. Yeah, again, we're not going to be talking about the instrument drifts nor the acceleration. So this is just a trend. All right, so I just go directly showing the result over here. There's no tide gauge trend posted on this figure. I wish I had. But this is like, for example, when we start something like 190 or 200 tide gauges. And then we do a reconstruction, like we described briefly as before. We use a priori glacial isostatic adjustment models. Yeah, we use ICE6G to correct for tide gauge sea level trends, so make it geocentric. Then you do the reconstruction. So the reconstruction is actually all the way from 1952 to 2002. So this is actually the next step is iterating, solving for that tide gauge vertical motion and tide gauge so that everything is consistent. And we try to use the robustness of both data sets. So global mean sea level trend is about 1.75 millimeter per year. So I want to show you the two different, so we actually do an experiment at the top where you see the red is reconstruct the sea level, like using 29 years. So the full spectrum of whatever we have from 1991, meaning altimeter era. And we use all the tide gauge that we pick the longest, actually from start 1952. Actually, they are longer versions of tide gauge. So we just do an experiment, we just do an experiment also. Like we use half of the, roughly half of the altimeter data in the reconstruction. So just want to see its effect. So its effect actually is sort of tremendous. It's 14 years. And then you could see that the trend actually changed, not to mention any other signals. And then the correlation of it, we computed it. I think there are a lot of differences. You could see, let's see, for example, here. So the red seems to have the 29-year altimeter when you use in the reconstruction seem to have higher amplitudes. So we just need to further study this. All right, so this is the same time series you saw where the two mean sea level trend. And then we actually compute a correlation over here for the two different reconstructions. You can see it's kind of complicated. Most of the time it's correlated, but there are times that they are not. If you could see for example, in Antarctica. Again. So anyway. Okay, over here, and as certain regions, they are not colored. So that's just a sensitivity work showing the different reconstruction using 14 years versus 39 years of radar altimeter data. All right, so we did a comparison. For example, the first comparison uses the song, our French colleagues' data at GPS at high gauges. So you see the correlation. So the first iteration, meaning GIA, was used. And the second comparison is that we had iterated rates. So basically over here, sorry, the second comparison, you can't see it, is from the Nevada. So it's a global GPS data to compare. So let's concentrate on the left one. You could see that the iterated vertical motion is the blue circles. So versus the start, which is obviously a start, which we assume that GIA is the source of the glacial isostatic adjustment is the source of the vertical motion, which is obviously not true. So some of the data are actually after the iteration are better. So again, this on the right, we just use the other set of GPS data, which are not necessarily close to the high gauges. So, but if you look at the statistics over here, it doesn't quite seem to be a lot of improvement, except the correlation improved from 0.63 from about 0.59. So the next step is that we try to actually verify the sea level. The sea level has to be changed. So the one you saw is before the adjustment, basically using GIA corrections. See the way to look at it is this is the original tide gauge. You see the color. It's not the same as the sea level. It should be measuring the same. So you see the reconstruction over here in the ocean, and the tide gauge is still the sea level trend, but correlated with GIA. So, all right, so this is the Gulf of Mexico, Northern Gulf of Mexico. You see that after the iteration, the trend looks slightly better, I guess, especially on this station over here. So if you take there's another station, don't know whether you should see it, is a start. So this is an independent verification, meaning that the tide gauge record is actually too short that we did not use it in the reconstruction. So you could see that we didn't compute a correlation, but with naked eye is agreeing pretty well. Actually, you could stretch it, look at the a shorter span and expand the scale. It's pretty well. So basically, this is like comparing the tide gauge, which we did not use in the reconstruction, versus the reconstruction, which is the blue time series. And this is all the way from 1952 to 2022. So another case is the US East Coast. So let's see. So again, we see some of these slightly orange. I don't know whether you could see that. Pointer is not quite working. Right here, yeah, right there. So we took another independent tide gauge and compare. So primarily, you could see that the tide gauge actually does not agree very well with the reconstruction because of the higher amplitudes. But overall, the trend and everything else seems to be consistent. So we have many other cases, but we just wanted to So I think this is the final case. So this is United Kingdom and Spain cost. So before adjustment, you could see that there are some stations that are not consistent, some tide gauge trends, they are not consistent with the sea level reconstruction. So after the iteration, you could see that at least with ice, it's very more consistent. And then we have a independent verification of a station near the Spanish coast over here. And actually the amplitude, the wear is still higher, but so this is one of the better cases of comparisons. So the final case is in a South China Sea. Actually, I wasn't very clear with it. Okay, the station is over here, and this is actually a dependent case. In other words, the tide gauge data is already used in the reconstruction. So you could see that the reconstruction will extend the tide gauge, will extend the tide gauge time series back from 1952. So I think this is the end of my talk. So in conclusion, this is still a work ongoing. And the next thing we wanted to try to do is actually try to squeeze in, to see whether we could actually detect regional acceleration, sea level acceleration, which in my opinion is still going to be very difficult, primarily because the long period signals in the ocean. That's totally, the tide gauge is the longest trends, about 150 years, 200 years. However, there's only a few of them in the ocean that we are unable to actually sense all the information, even with reconstruction. And the other problem was already published, saying that there could be drifts in the instrument for altimeter, for example, radiometer in the altimeter, and so on. So thank you.
Thank you. Any questions?
Yeah, thank you, Sergei. It's nice to see that you picked up the reconstruction method again. It was a while that everybody was excited about it and then was dropped by the wayside. And luckily, you're coming back to it because I think it still has potential. What you're saying about drifts, I think we have very much covered that by now. That in those 30 years and for example, the work that Ergoliat has been doing, comparing it to tide gauges, current day tide gauges, of course. I think we're pretty sure nowadays that we can capture the drift, so we don't see any significant drifts anymore. Also, the topics data has been now updated, so I think we have a good handle on that. So I think that's less of a worrying. What I really would like to see, and you said that you're going to look at that, is indeed, is it viable that we go all the way back as far with tide gauges that indeed were only very few in the beginning? And you were more worried about drift, but wouldn't the change of the dynamics or the climate, the change of the climate over time not be an issue with going all the way back? Because the modes that we have now in the ocean could have been created by more recent climate changes than the ones before. So we will never be able to fit the current modes to the let's say the 1850s or 1950s years. Then am I right to be concerned by that?
That's an excellent question. So that's the one I want to talk to you about also on the drift. So for example, I did not want to go into details. The Matt King had a Science and Nature paper using GPS to estimate the altimeter drift. The issue could be the GPS is not really, near the tide gauge for the same reason I talked about, and did not detect the same motion. So because tide gauge could be on the sediments in a different motion. So I saw Ranko's Nature scientific report for the drift. It's really a good paper. So that's one reason I want to talk to him. Didn't have a chance before my talk. So his question on the different modes is absolutely correct. The details that I didn't want to talk about because, like I say, this is work ongoing. A student is still working on it. So I should say that all the reconstruction, sea level reconstruction method assume the pattern is stationary. But guess what? For example, PDO is not. It's not stationary. And but it could be, well, it's not stationary, meaning that our data may not be able to produce a pattern that's stationary. So we're still working on it. We're not sure whether it's actually not stationary because of Ranko mentioned the pattern changes, or the reconstruction method, the EOFs, the cyclic EOF could be better to tie it down. I think we still don't know the answer yet. I think the worry I have is basically the long period signal. You probably know Don Chambers et al. Had a paper saying that if there's a 60-year signal in the ocean and you cannot really get accelerations. So, but people are putting out acceleration numbers. So we really do not know. And a signal could come from actually the core. You see, maybe was it Science and Nature paper saying that the core started slowing down, but it has a 70-year signal. 70-year signal, 60-year signal is in the carbon dioxide, ocean model maybe, and elsewhere. So some signal are not the harmonic driven, meaning you have 18.6-year tides, you make it 2 times, 3 times, become 60 years on a harmonic signal. But some of them could be coming from somewhere else. So I think that would be the interest.
Thank you. Okay.
Okay, that's more. Thank you. CK, thank you for the impressive work with this long-term sea level reconstruction. Will be, you know, for the sea level budget closure discussion is for the related to the climate change. Or these changes many of the or some of the conclusion, or have you have any thought to use this improved reconstruction to improve those work? Or
so you mean ocean model?
Well,
right.
Like the ocean height and sea level and
yes.
the mass change of the ocean.
Yes.
So will this change some of the conclusion?
Yeah, I think this is another good question. I did not go into details. A lot of reconstruction from, for example, from John Church and other people uses ocean model. And we deliberately try not to get into ocean model, just data driven for now, maybe Ranko. I think Tony mentioned probably the thermal, right? The thermal. So we're talking about total sea level. Thermal is another issue over here, and there could be potential of, I'm speculating, for example, using 20 years of satellite gravimetry data, which is mass, and do a reconstruction. But there's no other instrument measuring ocean mass for longer than 20 years. Maybe the ocean model has the data, so that could be another idea, just to try the consistency. So I don't know whether I answer your question. It's a difficult problem. So the thermal obviously changes. We think it changes from some 10, 20 years ago for the trend to now.
Okay. So thank you again.
Thank you.
So this was the last presentation of this session, and we can move for a break before discussions.
Yeah, I'd like to thank the chairman, especially the one that did the long run. So now we can have a coffee break and look at posters while we have a coffee break. And in 20 minutes, we come back here, and then we start the most important part. It's to brainstorm on what we've seen and on the seed questions that were prepared by the chair. So back here in 20 minutes. Thank you.